In this tutorial, we will be discussing the definitions of acids and bases. An acid has a sour taste. They react with active metals. They react with carbonates, producing carbon dioxide. They turn blue in litmus red. And they react with bases to form ionic salts and neutralization reactions. Bases are also known as alkalis. They taste bitter. The solutions feel slippery to touch, such as soap. Red litmus turns blue when in contact with a base, and they react with acids to form ionic salts, once again in the neutralization reaction. The Arrhenius definition is the most basic definition. It was the original. According to Arrhenius, an acid ionizes in water to produce hydrogen. So acids will always be giving off that hydrogen. And here we have a hydrogen right here that's being given off. Bases dissociate in water to produce OH minus. So NaOH produces this OH minus when you put it in water. However, because it's the simplest, it doesn't explain everything. They don't explain why substances like NH3, sodium carbonate, and sodium oxide dissolve in water to form basic solutions, even though they do not contain hydroxide ions. They also don't explain why molecular substances like carbon dioxide dissolve in water to form acidic solutions, even though it doesn't contain hydrogen ions. Acid-base reactions that take place outside of the aqueous solutions are also not explained. And that brings us to the Bronsted-Lowry definition. This is the most general theory for common aqueous acids and bases. Acids, once again, donate the hydrogen ion. It's similar in definition to what was presented by Arrhenius. But the bases are different. Instead of being an OH minus donor, such as Arrhenius said, it becomes a hydrogen acceptor. This broadens the Arrhenius definition for the base, and it answers the questions to the non-hydroxide bases that Arrhenius theory cannot explain. So for instance here, on the top, H2O, H is donated, and OH is left behind. Therefore, the water is an acid. And this one, we have NH3. By definition now, bases accept hydrogens. So NH3 becomes NH4. That positive is from the positive charge of the hydrogen. Ammonia, NH3, is a base in water, and while water is the acid. So if we look here, NH3 becomes NH4 plus. It accepted a hydrogen in the process, making this the base. Water here went from H2O to OH minus. It lost the hydrogen, making it the acid. The NH3 and NH4 is a conjugate pair. It's related by the gain and loss of a hydrogen. So here it's a base. The reverse of that, once it's reacted, is the conjugate acid, and they pair them up. You can do the same thing with water. Water is the acid. OH minus would then be the conjugate base. Every acid has a conjugate base, and every base has a conjugate acid. In an acid-base reaction, the original base becomes a conjugate acid in the reverse reaction, and the original acid becomes a conjugate base in the reverse process. Each reactant in the product it's called a conjugate pair. Each reactant and the product it becomes is a conjugate pair. So here's the reactant, here's the product it becomes. We pair them up. This lost the hydrogen, so this was the acid. Once it's lost the acid, or once it's lost that hydrogen, it's now the conjugate base. H2O becomes H3O. It gained the hydrogen. Therefore, because it gained a hydrogen, it's the base, and this would be the conjugate acid. Down here, HCO3 minus went to H2CO3 minus. It gained a hydrogen in the process, making this the base, and therefore this the conjugate acid. H2O went to OH minus. It lost a hydrogen. That means this is the acid because it lost the hydrogen, and this is the conjugate base. Write the formula for the conjugate acid for the following. So, that means this is the base, and we're writing the conjugate acid. So, a base gains a hydrogen. So, H2O becomes H3O. NH3 becomes NH4. Notice this plus here is from the plus up here. CO3, instead, it'll be HCO3. Instead of -2, we're going to add 1 to that to make it a -1. H2PO4 becomes H3PO4. It's a -1. We're adding another 1 to cancel it out. And then F becomes HF, a -1, plus 1 from the hydrogen makes it cancel out as well. Alright, so now let's write the formula for the conjugate base, which means these are all reacting as acids, which means these are all going to give up a hydrogen. So, H2O becomes OH. We're getting rid of a plus, so 0 minus 1 is -1. NH3, we're going to lose one of these hydrogens. NH2, once again, it's originally neutral. We're losing a plus sign, so it's going to have a minus. H2PO4 minus, we're going to lose one of those hydrogens to be HPO4. We're starting off with a -1. We're getting rid of another one, so it becomes a -2. Identify the Bronsted-Lowry acid and the Bronsted-Lowry base, the conjugate acid and the conjugate base in each reaction. We have H2SO4 on the left-hand side. We have HSO4 on the right, so these two are going to be paired up. In this process, it went from H2 to H1. Therefore, this lost a hydrogen. So therefore, this is going to be the acid, making this one over here the conjugate base. H2O is going to H3O. Going to pair those up. It gained a hydrogen in this process. Therefore, that would make this the base. And this would be the conjugate acid. Down here we have HCO3 going to H2CO3. We're gaining a hydrogen. Gaining a hydrogen means it's the base, which means this would be the conjugate acid. You have to compare the left and the right side to determine what's going on. H2O is going to OH. It lost a hydrogen, meaning this is the acid. So this must be the conjugate base. Let's do a couple more. C5H5N is getting paired up with C5H5NH. We've gained another hydrogen here, which is making this the base, and thus this one the conjugate acid. H2O is getting paired with OH. It's going from H2 to H1. It lost a hydrogen here. Therefore, this is the acid, and this would be the conjugate base. Down here we have H and O3 going to NO3 minus. We've lost a hydrogen here, making this the acid, and this would be the conjugate base. And then H2O to H3O, We gained a hydrogen, making this one a base, and this one the conjugate acid. And those are your definitions for acids and bases, as well as conjugates.